What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into CI/CD, IaC, and programming concepts for data pipelines. Let's get into it. Your pipeline works on your laptop, you push it to production and it breaks. Nobody can figure out what changed, nobody can roll it back, and the person who built it clicked their way through the Amazon Web Services console 6 months ago. That's the problem this video solves. By the end, you'll know how to take a data pipeline from a script on your laptop to a versioned, automatically deployed system on Amazon Web Services. We're covering continuous integration and delivery, infrastructure as code, SQL optimization in Redshift, basic Git, and Lambda tuning. That console-built pipeline is the philosophical problem this whole topic addresses. A pipeline you wire together by clicking is a pipeline nobody can rebuild, nobody can review, and nobody can roll back. The moment your glue job, your Lambda, and your step functions workflow become real production assets, they need the same treatment as application code, written in files, stored in Git, tested automatically, and deployed by a pipeline of their own. Picture this: someone accidentally deletes a glue job at 4 in the afternoon. If that job was clicked together in the console, you're spending the next 3 hours reconstructing it from memory and screenshots. Now picture the same pipeline defined in code. You rebuild it in minutes, you see every change in Git history, and rollback is one command. Compare that to the console version, where there's no diff to tell you what changed last Tuesday, and rollback means trying to remember what the settings used to be. That's the practical difference, and that's what the rest of this video teaches you to actually do. Here's the 4-service chain you need to recognize cold. CodeCommit is the source, your Git repository, where the pipeline starts the moment a developer pushes a change. CodeBuild picks it up next, spinning up a temporary container to compile the code, run your tests, and package the artifact to S3. CodeDeploy takes that artifact and pushes it out, with blue-green or canary rollout patterns built in. The final stage is prod, your Lambda functions, ECS tasks, or EC2 instances that actually serve the workload. And wrapping the whole thing is CodePipeline. CodePipeline doesn't build anything and doesn't deploy anything. It's the conductor, it defines the stages, moves artifacts between them, and decides when each specialist gets to act. Think of it like making a movie. CodePipeline is the director, they don't film anything, they don't project anything, they just call action and cut. CodeBuild is the camera crew that actually shoots the footage. CodeDeploy is the projectionist who puts it on the screen. The director hands footage from one specialist to the next. That's the orchestrator versus worker distinction, and it's the one people most often get wrong. Quick note on CodeCommit. Amazon Web Services closed it to new customers in July 2024 and reversed that decision in November 2025. So it's back at full general availability. Treat it as the canonical source stage for exam purposes. In the real world, GitHub wired in through a CodeStar connection feeds the same downstream flow. Now let's talk about infrastructure as code. The pitch is simple. Instead of clicking through the console to create an S3 bucket, a Lambda, an IAM role, and a VPC, you write all of that in text files that's stored in Git. 3 benefits fall out of that. You can spin up an identical dev environment, staging environment, and production environment in minutes. Every change is auditable because it's a Git commit. And nobody ever has to ask in Slack which checkbox they forgot. Amazon Web Services gives you 3 flavors of infrastructure as code, and here's how they relate. CloudFormation is the foundation. You write YAML or JSON templates that describe your resources. It's verbose, but it's explicit, and it covers every Amazon Web Services service. CDK, the Cloud Development Kit, lets you write the same infrastructure in a real programming language: Python, TypeScript, Java, .NET, or Go. And SAM, the serverless application model, adds purpose-built shortcuts for Lambda, API gateway, DynamoDB, and step functions. The key insight: both CDK and SAM compile down to CloudFormation underneath. They're abstractions, not replacements. Same engine, different abstraction levels. Straight from the CDK documentation. When CDK applications run, they compile down to fully formed CloudFormation templates that are then submitted to CloudFormation for provisioning. That sentence is the answer to a very common exam pattern. If a question asks which service ultimately deploys the resources, even when the developer wrote the code in Python, the answer is CloudFormation. CDK is the front end. CloudFormation is the engine. One CloudFormation concept worth pinning down: nested stacks. A nested stack is a stack that lives inside another stack. The parent passes parameters down and reads outputs back. When you see reusable modular templates or hitting the template size limit, think nested stacks. The main reason a data engineer cares is ownership. The networking team owns the VPC template, the data team owns the pipeline template, and the two compose together cleanly through the nested stack reference. Here's the thing to internalize about SAM. It's not a separate deployment service. It's technically a CloudFormation macro, a transform line at the top of your template that tells CloudFormation to expand SAM's shorthand resources into full ones at deploy time. So when you write a few lines describing a Lambda function, CloudFormation does the real work behind the scenes. You'll see exactly what that shorthand looks like in the next scene. Here's a real SAM template for a Nexer retail-style ingestion pipeline. The transform line at the top is what makes this SAM instead of plain CloudFormation. Then look how compact this is. Amazon Web Services : serverless : function gives you a Lambda with its runtime, handler, memory, and an SQS trigger, all in about 10 lines. Amazon Web Services : serverless : simple table is a DynamoDB table in one line. Notice reserve concurrent executions set to 1. That caps this loader at a single concurrent invocation, which protects DynamoDB from a burst of writes. The same setup in raw CloudFormation would be roughly 50 lines. Here's the decision rule. If a question mentions Lambda, step functions, and DynamoDB deployed together as one serverless unit, the answer is SAM. If a question mentions defining infrastructure in a familiar programming language, Python, TypeScript, or Java, the answer is CDK. And if it mentions raw control, legacy templates, or multi-account stack sets, the answer is CloudFormation. All three end up as CloudFormation at deploy time, but the question is asking which abstraction the developer writes. Switching gears to SQL optimization in Redshift. The single most useful tuning tool you have is the explain command. Put explain in front of any query, and Redshift returns a detailed execution plan, broken down step by step, including subqueries, joins, and a cost estimate for each step. When a query is slow, explain is how you find out why before you start guessing. Here's a real Redshift query plan for a Nexer retail order summary. Read it bottom up. The planner scans the customer dimension and builds an in-memory hash from it. Then it scans fact orders, applying the date filter at scan time. That's the filter line right under secscan. Then it joins the two with a hash join, and the ds-dist none tag is good news. It means the data is already collocated, so no rows have to move between nodes. Finally, it aggregates. Two things to notice. The date filter pushed down to the scan and no data movement on the join. That's a healthy plan. Here's how to read what's good and what's a red flag. On the efficient side, a merge join means both inputs are already sorted on the join key, which is the fastest join Redshift can do. A hash join builds an in-memory hash from the smaller table, which is still very fast for most workloads. And a sequential scan is fine on small dimension tables. On the red flag side, A nested loop on large tables is the slowest join type and almost always a tuning bug. A sequential scan on a billion-row fact table means you're probably missing a sort key or a predicate. And anytime you see DS dist both or DS broadcast inner, that's data being shuffled between nodes, expensive. One more thing, if your plan looks weird, run analyze first. Stale statistics produce bad plans. The single most important SQL optimization concept is predicate pushdown. Picture a warehouse worker fetching boxes for a shipment. Without pushdown, they bring every box on the shelf down to the loading dock and then check the labels. With pushdown, they read the labels at the shelf and only carry the right boxes down. Way less heavy lifting. In SQL, that means you're where clauses belong on the base tables before the join, not in a filter applied to the joined result. A columnar warehouse like Redshift can skip entire blocks of data when a predicate excludes them, but only if you give it the chance to apply that predicate early. One more Redshift feature worth knowing: stored procedures. A stored procedure is a named block of SQL with PL/PG SQL control flow like loops and conditionals stored inside the warehouse itself. You create one with create procedure and invoke it with call. They matter for two reasons. First, you avoid client round trips when chaining several SQL operations. 5 statements from outside the warehouse means 5 network hops, but wrap them in a stored procedure and it's one call. Second, multi-step ETL logic, transform, validate, then merge, can stored in one version place inside the warehouse, instead of being scattered across application code. Now let's talk about Git, and let's keep this calm. The exam doesn't expect you to resolve merge conflicts or rebase branches. It expects you to know what 6 basic commands do, the mental model that makes them stick. Git is a shared Google Doc with time travel. Multiple people work on the same project, every save is a snapshot, and you can go back to any point in history. Here are the 6 commands worth knowing. Clone copies a remote repository down to your machine for the first time. Branch creates a new line of development, a sandboxed copy where you can experiment without touching the main code. Commit saves a snapshot of your changes with a label recorded only on your local machine. Now the other 3. Push uploads your local commits to the remote so the rest of the team can see them. Pull goes the other direction, it downloads everyone else's commits and merges them into your local branch. And merge combines 2 diverged branches back together, typically your feature branch back into main. That's the whole set. Clone, branch, commit, push, pull, merge, 6 verbs that cover the Git knowledge the exam tests. One subtle point that trips people up: Git pull and a GitHub pull request are completely unrelated. Git pull is a command line operation that downloads remote changes and merges them into your branch. A pull request is a GitHub feature for proposing and reviewing a change before it gets merged. Same 2 words, different worlds. The exam may use either term, and you should be able to tell which one is being asked about from context. 2 Lambda concurrency settings that sound similar and do very different things. Reserved concurrency is free. It fences off a slice of your account's concurrency limit, so a critical function is guaranteed capacity. And as a bonus, it also caps the function at that number, great for protecting a slow downstream database. Think of it like a reserved parking spot, yours when you arrive, empty until you do. And it's a 2-way fence. It protects you from being starved by a noisy neighbor and protects everyone else from being starved by you. Provisioned concurrency is the opposite trade-off. It costs money, but it pre-warms execution environments so there's no cold start. Choose reserved to protect capacity, and provisioned only when a cold start would break your latency SLA. If you remember one sentence from the concurrency discussion, make it this: reserved concurrency protects capacity and costs nothing. Provisioned concurrency eliminates cold starts and costs money. When a question describes protecting a downstream database or guaranteeing a function can scale, the answer is reserved. When a question describes a latency-sensitive API where the first invocation can't be slow, the answer is provisioned. These are the Lambda numbers worth memorizing. Maximum execution time is 15 minutes. If your job runs longer than that, Lambda is the wrong tool. Maximum memory is 10 gigabytes, and Lambda's CPU scales with memory, so bumping memory often makes CPU-bound functions faster and cheaper at the same time. Max/TMP storage starts at 512 megabytes by default, and you can raise the /TMP directory up to 10 gigabytes if you pay for it. Max container image size is also 10 gigabytes, which is what you get when you package Lambda as a container instead of a zip. And default account concurrency is 1,000 simultaneous invocations per region. Those 5 numbers cover almost every Lambda limit question. Lambda has 3 storage options, and the exam wants you to pick the right one for the scenario. The /temp directory is per invocation scratch space, handy for a CSV you're parsing, but it dies with the execution environment. Think of it as scratch paper on your desk. EFS is a mountable file system that gives you persistent storage shared across invocations and even across different functions. It requires the Lambda to be in a VPC, which brings some setup, but it's the answer when you need state to survive. And S3 is object storage for large datasets, bottomless capacity, but not mountable as a file system. One thing to remember firmly, you cannot mount EBS volumes to Lambda. If a question offers EBS as an option for Lambda storage, it's wrong. 2 VPC facts the exam loves, plus 2 quick side notes. First, when you attach a Lambda to a VPC, it loses internet access by default. It can't even reach public Amazon Web Services API endpoints. The fix is VPC endpoints or a NAT gateway. Second, if you need persistent shared storage via EFS, the function must be in a VPC. There's no way around that one. Now the side notes. Tiny /28 subnets cause network interface exhaustion at scale, because every concurrent execution claims an ENI from that tiny pool. And the old story about 10-second VPC cold starts is obsolete. Modern overhead is 50 milliseconds to 2 seconds. Here's the keyword to answer decoder. Orchestrate, build, test, and deploy means CodePipeline. Write infrastructure in Python or TypeScript means CDK Lambda plus step functions plus DynamoDB as one deployable unit means SAM. Reusable modular templates or template size limit means CloudFormation nested stacks. Show me the query execution plan means explain in Redshift. And persistent storage shared across invocations means Lambda plus EFS, which requires VPC attachment. 3 ideas to carry forward. CDK, SAM, and CloudFormation are the same engine at different levels of abstraction. Pick the one that fits your team. Always run explain before you optimize a Redshift query. A sequential scan on a fact table tells you everything you need to know. And on Lambda, reserved concurrency protects capacity for free, while provisioned concurrency kills cold starts for a price. But here's the bigger picture. The data engineers who stand out aren't the ones who memorize the most SQL tricks. They're the ones whose pipelines survive a midnight outage because everything is versioned, tested, and redeployable in minutes. That's what this whole topic is really about. Now let's test it with a quick 5-question quiz. And that's a wrap on CI/CD, IaC, and programming concepts for data pipelines. If this helped you out, smash that like button and subscribe for more. See you in the next one.